In this I do problem, they give us the mass spectrum of a sample of a pure element. We don't know what it is, but they're asking us to calculate the average atomic mass of the element. Now, the blue numbers here represent the percent abundance. On your note sheet, you have a formula for average atomic mass, and you're given relative abundance of an isotope. Now, relative abundance is just the percent written as a decimal. So the calculation's fairly easy, fairly straightforward. We're going to go ahead and calculate the average atomic mass. So I'm going to use AAM for average atomic mass. And it's the sum of the relative abundances times the mass of the isotope. So this first one, this 93.26%, is for isotope number 39. So whatever this element is, we know it's between 39 and 41, but most of it is 39, so it's going to be really close to 39. That's going to give us, let's see, as a decimal, that should be 0.9326. And we're going to multiply that by its um, mass, which is 39. And that's 39 AMUs, atomic mass units. We're going to add to that the second one. And this one's so tiny, you can barely see it. I actually drew that in as a decimal. That's going to be 0.0001. And its mass is 40 AMUs. So in a typical sample, there's hardly ever any of that isotope. And then our third isotope we see here is about 6.73% of, let's see, 41. So that's going to be 0.0673 times 41 AMU. So when we calculate that out, we get approximately 39.1347 AMU. Significant digits really don't matter too much right here because we've got a bunch of different things going on. But if we look at our periodic table, if we look at what element has a mass that's closest to 39.1347, it looks like the identity of this element is probably potassium. Oops, not potassium, potassium. There we go. And the symbol for potassium is K. That's it.